So as this name suggests, integration by recognition, we're going to learn a very powerful and useful set of recognition integrals, such that if you end up with an integral that you recognize that takes a certain form, you can just apply a very standard result. Now, as we're going to see, technically this section is redundant because there's another method that we will learn called integration by substitution that will get these integrals done, except as you'll see later on when we cover some of the longer techniques such as parametric integration, integration by substitution that I've mentioned, they're quite long already. We have to do a lot of manipulation to sort out the integral, and when we have that integral simplified after 10 or 15 lines, you'll find that it's actually quite useful that if it fits one of the following forms that I'm going to go through, you can literally just finish off the integral in one line. It's very, very useful. Instead of having to apply another technique called integration by substitution to get the job done. In order for you to see these results, that they're not results plucked out of thin air, we're going to see where they come from through differentiation. So what I'd like to do is a very quick exercise, is I'd like you to differentiate the following two functions and see if you can spot a pattern as to how we might generalize an integration result from these differentiation results. So I'd like you to have a go at differentiating the following two functions. Have a go at differentiating ln of x squared minus 3x plus 4. See what you get for dy by dx. And then have a go at y is ln of e to the 2x plus e to the minus x. So spend 60 seconds, shouldn't take you very long at this stage, to find dy by dx for those two examples. And then have a think about, given what dy by dx is for these examples, if you can generalize a result from the types of results you get here, integrating back to the original function. See if that gives you a clue as to what I might have to say next. So pause the video if you haven't sort of finished that off. So we know that if you have to differentiate ln of a function, it's 1 over that function, because ln of x differentiates to 1 over x. But because the inner function is not just x, we have to multiply by the derivative of this function, which we learnt in differentiation. So the answer to this one would be dy by dx is 1 over that quadratic, x squared minus 3x plus 4, multiplied by this derivative, the derivative of x squared minus 3x plus 4, which is, of course, 2x minus 3. Let's sort that out. So let's write it over here. Okay, let me call this the yellow equation and the green equation. Okay, so the yellow equation I'll do over here, which is dy by dx. And if 1 over that multiplied by that, that will just fly to the top. So you get 2x minus 3 over x squared minus 3x plus 4. What do I want to do with that? Well, let's see. Okay, let's do the other one. So the green equation, okay, similarly, dy by dx would be 1 over this. So 1 over e to the 2x plus e to the minus x, multiplied by this derivative. Okay, just take care of the exponentials. That would differentiate to 2e to the 2x. Again, use a bracket. And this will bring down a minus 1. Again, stick that bracket on the top. So fully simplified answer would be 2e to the 2x minus e to the minus x over e to the 2x plus e to the minus x. Now, if you haven't already, maybe pause the video. Think about something special. When you look at this dy by dx over here and this dy by dx over here, do we notice a pattern between the numerator and the denominator? Okay, if you want a step to think about that, pause the video. What you should have recognized is that when we sorted the dy by dx out for both cases, what hopefully we've noticed is, if you consider the denominator, the numerator is just the derivative of the denominator. Look at this, denominator, e to the 2x plus e to the minus x, differentiate that, it goes there, differentiate that, it goes there. Same here. Differentiate this, you get 2x minus 3, that's on the top. Okay? And we could generalise why that would happen. It's not a coincidence that happens. Okay? So if you haven't got that down, please just get that down, because I'm about to rub it off. We could generalise this for any. Well, I just chose those two functions. If we generalise it to ln of any function, we will see that we're always going to get the derivative of whatever's inside the ln over the original function itself. Let's see why that would always happen. So, why is ln of any function? Doesn't matter what the function is. Let's just call it f of x. So now let's do this in general. We shouldn't be afraid because I'm using a general function. dy by dx will be 1 over that function, multiplied by the derivative of whatever's inside the ln. Now I don't know the function, it's just general f of x, but I do know that the derivative of f of x is f dash, f prime. Okay? And therefore, that ends up being f dash x over f of x. Now, we've just discussed differentiation, right? We are now learning integration. What's this got to do with anything? Well, from this result, we have a very, very useful tool. If ever you're integrating something that looks like the derivative over the derivative, something that looks like the derivative of the denominator as the numerator, in other words, whatever's on the denominator, if you differentiate that, and it's looking like that's what's on the numerator, i.e. it looks like f dash over f, well, then we can integrate backwards to say it's actually just ln of the denominator. Now this is going to be very useful because quite a lot of integrals you meet are of this form. To start with, let us just generalize this result. This is what I would call the first recognition formula you need to know. Again, if you end up in the exam and you get a quotient, okay, that fits this form, okay, it might not quite work. If it doesn't work, there's 5, 6 other integration methods that we will learn. But if it does fit this form, I can just write down the answer. It's just a ln of the denominator. So let's formalize this now. Okay. So we saw that if you have ln of any function, you end up with f dash over f, the derivative of the inside of the ln over the original function that was in the ln. So in other words, we're talking from the integration point of view. So we have the very important formula, okay, which you should write down. If you spot that you have f dash over f in your integral, if the integral somehow ends up being something like this, it's simply ln of, okay, f of x, and we should be strict about this. It's going to be ln of the modulus of f of x, because remember when we were reversing the ln differentiation rule, we discussed just like 1 over x differentiates to ln of mod x. It's the same sort of logic applies here. So that is an important recognition formula. If you have the derivative over the function, you can just apply this rule. And some very, very famous integrals come out from this rule. Okay, so let me show you one example. Okay, one example of applying this rule, not necessarily a famous result, but one. So for example, let's say you are integrating 2x over x squared plus 1. Okay, you look at that integral and you'll struggle to apply any of the other methods we'll learn in regular maths year 2 to do this integral, apart from substitution, which I said substitution can solve all of these recognition formulae, integrals, but it would take longer. Now, so 2x over x plus 1, let's have a look. Well, look, if the denominator differentiates to the numerator, that's the way to think it. Does the denominator differentiate to the numerator? It does. X squared plus 1 doesn't differentiate to anything. X squared differentiates to 2x. It fits the formula. Therefore, I can just write down the answer. It's a one-liner. Ln of modulus x squared plus 1 plus c. Now, you'll notice for this example, x squared plus 1 doesn't need the mod, because x squared is positive, or minimum 0 if x is 0. Okay? But you add 1, x squared plus 1 cannot be negative, and it cannot be So you don't need the modulus. But if you write the modulus, even if you don't need the modulus, it's not wrong. Okay? But I don't need the modulus. That's a rare example. Okay, so just put the modulus in. Okay, here's another example. If I've got 2e to the 3x minus cos x on the bottom, and I've got 6e to the 3x plus sine x. Okay, looks a really horrible integral, but actually, just take a step to think, does the denominator differentiate to the numerator? It does. Okay, that differentiates to that, cos differentiates to minus sine, so that minus becomes a plus, it works. Great. So that is the first recognition integral. I'm going to go through all of them, and then we're going to look at some examples. Okay, so that's the first important result to think in your mind, to look out for. Does it fit this form? Now, I gave you the scaffolding, I gave you the steps in terms of the thoughts that we were going through into what we were trying to achieve. What I want you to do now is to go through the whole process yourself for the next type of recognition. So what I'm going to do is I'm going to give you two functions to differentiate. I want you to look at the results and see by yourself if you can generalize what the next family of integrals we're looking for. Generalize it to an f of x. So I'll give you two examples, you differentiate the examples, then generalize, see if you can spot a generalized pattern to resemble those integrals, and then come up with a rule, a second rule. So let's see how you get on. So I would like you to integrate e to the cos x, and I would like you to integrate e to the x squared plus 5x cubed. Okay, I'd like to have a go at those two examples, look at the results, then generalize those differentials, generalize it, and see if you can come up with a new recognition formula. Okay, it's a different type of integral recognition that you need to spot. Right, pause the video if you haven't quite finished, because I'd like to go through this. So, e to a function we know differentiates to itself, but you have to multiply by the inner derivative, the derivative of cos x in this case, which is minus sine x, and we know it's always neater to stick that out in the front. So we have minus sine x e to the cos x. Now, here we have e to the same thing, x squared plus 5x cubed. Okay, the e function differentiates to itself. And then you have to multiply by this derivative, which is 2x plus 15x squared, which is 2x plus 15x squared times e to the x squared plus 5x cubed. Right, that was the easy bit done. Now the harder bit is generalising that. So now what happens here? You can see we've got e to some function, that's what was going on. We've got e to the something. Okay, cos x, x squared plus 5x cubed, it could be anything. So if we generalise, we've got y is e to the fx. Now what happens? I think this result's potentially more intuitive, because it's a bit obvious what happens. Then dy by dx is itself, but the inside of the e needs differentiating. It's the chain rule. So you multiply by f dash x. Right, what do I want to do with that? Generalise it to integration. If I have e to the something, and itself, the e term is multiplied by the derivative of the power of e, or the inside of the e, then that, okay, will integrate to that. So if you have an e to something, multiplied by the derivative of the e, then it just integrates back to e to the f. It's just the reverse of this result. And formally, as an integral recognition formula, we're now the second of three recognition formulae that we are going to formalize. This is now needs to go in the big box. Okay, this is the second recognition formula. we say as follows. E to the function multiplied by the derivative is e to the f of x plus c. And if you have something of that form in the exam, it's a one-liner. I can just write down the answer. That's the second recognition formula. It's very important to have in the back of your mind that if it matches, if it ticks the box, basically looks like that, great, you can write down the answer. The third one, again, I'd like you to go through, you know the drill by now. I'm going to give you a couple of differentials to do, try and generalise it to f of x, and then try and come up with a formula for integration. There's a little bit of tidying up you could do here, but let's see, have a go. So what I'd like you to do is to integrate the two following functions. Y is 3x squared minus 5 cos x to the power 5. And number 2, y is the square root of tan 2x plus x. Okay, differentiate those two following functions, see what they have in common so you can generalise it, and then reverse it to find a rule for integration. Okay, if you didn't pause the video, please pause the video because we're now going to go through it. And it's always nice to see if you could form this by yourself. So, y is 3x squared minus 5 cos x to the 5. Got a bracket to the power 5, so just use the power law. Okay, chain rule again, bring down the 5. Keep the bracket as it is. And you multiply by the differential of the bracket. Okay, standard chain rule, which is 6x plus 5 sine x, which becomes 5. Okay, not really a lot to do here, just you can keep it like that. Yeah. Just attempting to get this in one line. Okay? You could have had that bracket first, it doesn't really matter. Right, over here, obviously the first thing to do is to rewrite that square root as the power of a half. And I'll just pop down here, dy by dx, again, same, you can see it's the same thing, same type of thing. Bring down the half, keep the bracket the same, multiply by this derivative, which is 2 sec squared 2x plus 1. Okay, now that process, the specific results I'm not particularly interested in, it's the process. So what's happened here? Once we change that square root to power of a half, we noticed that we've got a bracket to a power. Okay, the inside function of the bracket varies, it doesn't really matter what it is to be honest, but it's a bracket to a power. So what we see is that if I have y is f of x to the power of n, then dy by dx, bring down the power, keep the base of f of x the same, reduce the power, but of course f of x is an inner function that needs differentiating. And now in terms of reversing the integration, from here that follows that horrible thing, but we'll be able to process that in a little bit better in a second. This function here, n times f of x to the power of n minus 1 times f dash x, integrates to this. First of all, that's a constant. Okay, we've seen already with integration, you can take constants out, you can, right, so if this integrates to that, I can divide both sides by n. So that, okay, will integrate to that divided by n. So I could say that the integral of f of x to the n minus 1 times f dash x would be f of x to the n divided by n. I'm just going to make one change to that. What we notice here is that the f of x to the n minus 1, that power goes up there and it goes up there. So instead of instead of writing n minus 1 to n, I'm going to make that n and these n plus 1. It doesn't matter. I just need to know that the power goes up. And the reason we do that is because we're looking from the integration point of view. I don't want to start thinking about n minus 1s in the integral. Okay? It'll be easier for us, as you'll see, to turn that into an n. Okay? So effectively, what we need to recognise here, it's definitely the hardest one to think about, is that if you've got f of x, a function, to some power, a fixed numerical power, times the derivative of just the function. That's the sort of thing you need to look out for. Okay? And again, we've proved it through differentiation. Now let's formalise the result. The third and final recognition integral you need to know is as follows. The integral of f of x to the power of n times the derivative of just the f of x. You're ignoring the n. You're just differentiating the f of x. Will integrate to 1 over n plus 1. Okay, multiplied by plus c. And you can see through differentiation that clearly works. Okay, by chain rule. Okay, if you bring the n plus 1 down, it will cancel the n plus 1, leaving me with a coefficient of 1. Reduce this power down to n, and then times it by the inner derivative. Okay, this differentiation that I went through with you is just to show you where these formulae came from. Okay, but ultimately you just need to be able to use such a recognition formula. So let's just see an example of where this would come up. Okay, because it's nice to talk about this theoretically, but let me give you an example. Okay, so an example would be root 3x squared plus 1 multiplied by 6x. Okay, remember you have to be creative how you can have f of x to a power. It might not be in your face, some bracket to a power. Remember, square roots, okay, 1 over something, that's the power of minus 1. Okay, if you have something that feels like it's something to a power, or that can be written as something to a power, and the f of x itself is differentiated and multiplied together, it fits this form. So let's just put all the pieces together. Here, f of x is 3x squared plus 1. The power on f of x is the root, so n is a half. And the f of x, which we already wrote down as 3x squared plus 1, when you differentiate that, you get 6x. Again, it needs to, all the jigsaw pieces need to be there. Okay, if that was 6x squared, okay, it's no good, it doesn't work. Have to think about something else. So if you put all those into the formula, remember the actual integration result, you don't need f dash, it just needs to be there in the integral. The answer is 1 over n plus 1, n was a half, so 1 over n plus 1 is 1 over 3 over 2. So 1 over n plus 1 is 2/3, it's 1 over 3 over 2. F of x we said is this, and add 1 to that, you get 3 over 2. And it's easy enough to check. Bring this down, 3 over 2 times 2 over 3 is 1. That stays the same. That reduces to a half, so that's where the root 3x squared plus 1, okay, and then times by the derivative, which is 6x. Okay, let me show you another example where this might come up. Might be a bit harder to see. You've got cos x over root sine x. What's that got to do with this? So remember, you have to think. You have to think. That's not exactly in that form as it stands, but a little bit of manipulation, and it can be. So even though this doesn't look like it could do anything to do with the quotient, okay, you can rewrite a quotient so it looks like that. How? Well, look at this, the root sine x on the bottom. The root sine x on the bottom is sine x all to the power of a half. But if I want to bring it up, so this doesn't really allow for a quotient, it doesn't, it's not a quotient as it stands, you could rewrite this as sine x to the power of minus a half times cos x, and then it ticks all the boxes. F of x to the power of n, and that is the derivative of f of x. Look. F of x is there, n is there, f dash is there. You apply the rule and you actually get quite a nice result. It looks quite a horrible integral, it's quite nice. What's the result say? F of x, which is sine x, increase the power by 1, you get a half. Let's put a bracket there. Divide by that increased power, and divided by half same as 2. And if I wanted to, I could write that as 2 root sine x plus c. Quite a nice result. Quite a nice result. Let me now summarise the 3 recognition formulae so we can see them together. Because you need to, I can't guarantee which one will apply. You have to make that decision by yourself when you're posed with a certain integral. Okay, these are the 3 special integrals. So if you ever find yourself looking at an integral that fits the form denominator and differential of the denominator as the numerator, right, we can apply this rule. Number 2, e to the something times the derivative of the inside of the e. You can apply this rule. And number 3, sometimes you requires a bit of manipulation to make it look like this, but if you've got f of x to the power of n, f of x to some power, so think roots, that can be written as a power, maybe 1 over, right? Sometimes the difference between this and this, okay, is very subtle, very, very subtle, okay? Times the derivative of whatever you choose to be your base, okay, an algebraic base. Then you can apply this rule, f of x n plus 1 over n plus 1 plus c. So make sure it's really important at this stage you have this on one piece of paper. We went through 1, 2, 3 separately. Now what I want to do is I want you to have this down on a piece of paper. I'm going to put up some integrals. I want you to decide how to manipulate them to use whichever one of these rules applies. I'm going to make some of them similar, very, very similar. I'm just going to change them slightly to make you see why specific properties of each of the 3 rules is quite important. Okay, so I'm going to put up a few integrals now. I want you to have a go. When you've spotted which recognition formula, you will appreciate later on how this is a real saver. Because once you recognise which one it is, it's 2 lines. Maybe 3 lines if you have a little bit of simplifying with the n plus 1. But really, 2 lines maximum. So I want you to have a go at the integrals that are going to pop up any second now. Okay, so have a go. We've got 4 integrals here. You have to decide which recognition formula applies. Try and recognise what f of x is, what n is, if it applies, and then have a go. So press pause, and when you're ready, press play, and I'll take you through. Okay, so to start with, you can see these are very, very similar. Very, very similar integrals. And just because it's a quotient doesn't mean it's the first law. F dash over f is ln of mod f of x. It's only that law if the derivative of the whole denominator is on the numerator. So let's have a look here. Do any of these look like that? Well, hopefully you realise the second one is. Because the second one is 2 minus cot x, and if you differentiate the whole of the denominator, what happens? Cot differentiates to minus cosec squared. The minus makes it cosec squared. It fits. That is f dash. That is fx, and it works perfectly, which means that one is simply ln the modulus of 2 minus cot x plus c. But this one isn't, because for that law to apply, it's very, very precise. It says the f dash over f, the denominator has to be completely differentiated. If I differentiate the denominator, I'm going to bring down a 3, there's going to be, then that's going to go down to a 2, you're going to have that bracket. Well, none of that, none of that you can see on the top. So what you have to recognise here is this, you have to spot connections. You have to say to yourself, when you see cosec squared, you have to say, well, that's the derivative of cot. So there must be some relationship between f and f dash here. But you have to play around with it. So this one here, you have to write as 2 minus cot x to the power of minus 3, multiplied by cosec squared. And now look, we've got number 3, rule number 3, recognition integral number 3. If you call that f of x, if you call this n, well then remember that's f dash. Look, 2 minus cot x we already saw differentiates to cosec squared. It fits the formula. I've got f of x to the power of n times f dash. Rule number 3 says that goes to f of x to the n plus 1 over n plus 1. Which means that this integral over here that I've rewritten is simply f of x to the n plus 1, so that minus 2 becomes minus 2, divided by minus 2. Remember, divided by minus 2 is much neater, written as minus a half, 2 minus cot x to the power of minus 2 plus c. So you need to be creative the way you think about these things. Now don't worry, it takes time to spot them. If you're looking at that and think, oh, it's a bit hard to see, with practice you'll spot it. Now this one is perhaps potentially the easiest one here, because straight away, for rule number 2, we're looking at recognition number 2 here, you see you've got e to a function times the derivative. It's more in your face, okay? It's much easier to spot that you can see that if you call this e f of x, and if you differentiate the f of x, half x squared, what do you get? You get x. It's right there. Fits rule number 2 perfectly. Remember, rule number 2 says the result is e f of x, so simply the answer here is e to the half x squared. Simple. But what about this one? Again, hopefully, by the same logic as I said, you can rule out number 1, f dash over f. Because although half e to the 2x plus 1 differentiates to e to the 2x, I'm not allowed to ignore this square root. So if I were to differentiate the whole of the square root, you certainly won't get that. So, sounds like it's a bit more like this one here, this sort of job. So what we do is we rewrite this as integral a half e to the 2x plus 1 to the power of minus a half, multiplied by that, which I'll put in a separate bracket. Now, what do we notice? Look, f of x to some power n, remember, it doesn't matter what the power is, and that is the exact derivative of this. Exact derivative of that. And therefore, supply the rule, f of x, the n plus 1 over n plus 1. This is f of x, that's going to go up to a half. You're going to divide by the half. So the final answer for that one is, let's write it here, is 2 a half e to the 2x plus 1 to the power of a half. That is the answer to that one. And again, if you just quickly differentiate that, by this stage that's a little bit of chain rule, but nothing more than that, you can see that that will differentiate to this. So you have to play around with it until it looks like that. Now, let me just make it clear, there will be integrals where you can't do this. Okay? But with a bit of practice, this won't take too long, and you'll be able to rule out if something can't be done, if it won't work for any of the integration recognition formulae. So there's 2 more things we need to do. There's a few famous integrals, I mentioned before, a few famous recognition integrals that come up a lot at the A level that you want to be able to spot. If you didn't spot any of these, you can actually do these by a method called integration by substitution, but it will take potentially 3 times as long, which is why, if you can spot them, you'll be saving yourself a lot of time. So let me show you some integrals that come up a lot. Okay? And some of them is obvious that it fits the form. One of them I think is particularly easy, but one of them you'll be like, hey, how does that fit any of the forms? So I don't want to say anything more because I want you to look at the integrals that are going to come up, and I want you to, again, apply the recognition formulae, whichever you think applies. Okay, here we go. Here's some 3 integrals. I want you to think, does a recognition formula apply? And if so, how do I apply it to look at these? And these are integrals that come up quite a lot at A level. So think how you could apply them. And when you're ready, press play, and I'll go through it. So the first one is actually the easiest, because it's already on a plate for you. Right, hopefully we can see straight away that I could write this as sine x squared times cos x. That's ready to go. I don't have to do anything more. F of x to the power of n times f dash. So according to the law, that would be sine x to the n plus 1, which now becomes 3, divided by n plus 1. And when you've done that, you might as well just bring the 3 back in and write it like we do for trig. So it's a third sine x cubed plus c. So that could be any power, right? Sine to the 10. As long as the cos is there, because the cos is the differential just of the base in that law. Now number 2, tan. You're thinking, what? Tan? It's always too simple, right? It's just one thing, it's not enough there. So again, as you'll see with integration, you need to start thinking how I can write things inside an integral. By the way, the inside of an integral is called an integrand. So how could I write this integrand? It's like something else. Now, hopefully the first thing you think about is tan is sine over cos. Now, tan being sine over cos could be written like this. Now, that's looking a little bit better. There's more meat on it, so I can, I can do more with it. But I've got a slight problem. It looks like rule number 1, because I've got f of x, but that needs to differentiate to minus sine x. I've got sine x. Cos doesn't differentiate to sine, it differentiates to minus sine. And minus, as you know, makes a difference, can't ignore it. However, if your recognition formula, wherever f dash appears, so you've got e to the f of x times f dash, you've got f dash over f, you've got f of x to the n times f dash, there's always an f dash. If the f dash is only wrong by a coefficient, so if there's an x that's different, or a completely different function, then you've got a problem. But if your f dash needs to be 2x squared, then you've got 4x squared. Or if your f dash is cos x, and you've got minus cos x. Or if your f dash is e to the 5x, and you've got 25 e to the 5x, you can sort that out. You can play around with it. So look what, okay? So if you've got a scalar multiple of f dash that you don't want, okay? The scalar multiple is a scalar multiple of f dash, you can fix that. What do I want that to look? I want that to look like f dash over f. So write it how you want it. Just, okay? So what do I want? I want this to be cos x over minus sine x. That's what I want it to be. Okay? But what do I have? I've got plus sine x. So what I'll do is I'll take a minus out. I'll rewrite sine x as a multiple of the derivative that I want. So all it means is you'll bring out a scalar multiple. Now that's okay. That works. Just check, do your integrals match? Is that the same as that? Yes, I've just rewritten it for my own benefit. And then f dash over f, so it must be ln of cos with a minus in the front. Okay, so this, let's go down here, that becomes minus ln mod cos x. And you can go even further than that. Right? We don't really like that minus sitting in the front. Why give your answer as a minus answer instead of a positive answer? Because it's a ln. Ln is a logarithm. You can bring the minus 1 up. Right? We're not dealing with arc cos. We're not dealing with the inverse. Cos of x to the power of minus 1 is 1 over cos, and 1 over cos is sec. So the most popular result for the integral of tan is ln of sec x. So the integral of tan is ln of sec x. So a simple integral that we haven't been able to do so far, right? We've just ignored the fact we can't integrate tan up until now. Well, this is one way to do it. Right, this one here, you see the powers, so hopefully you were drawn to the third recognition formula. The third recognition formula with f of x to the n. The problem is, what do you choose for n? Or more to the point, what do I choose for f of x? I've got a potential f of x to the n there. I've got a potential f of x to the n there. Remember, you have to choose f of x so that you've got f of x and f dash there together. So, if I choose sec x to be f of x, I've got a problem. Why? Because if that's f of x and that's n, if I'm choosing f of x to be sec, then I need to have sec times tan. I don't have that. I've got tan squared. Okay? We can choose f of x to be sec. That's the second method. We've got to play around with it a bit. Let's do the most obvious way, I think, is to choose f of x as tan. Because if I choose f of x as tan, so let's call that f of x, let's call this n, and f of x tan we know differentiates to sec squared. That works. F of x, n, f dash. And use the rule. What happens? F of x to the n plus 1, so the 2 becomes 3, divided by 3. So it's actually simply tan cubed x over 3 plus c. So just to round off this section, let me just give you some integrals that are recognition integrals, but the f dash won't quite fit. It'll be a scalar multiple of what you want. So remember, try and think which recognition formula applies. Okay, so try and fix what f of x is, what n is, what f dash is, and if your f dash is a scalar multiple of what you want, so it's a minus of what you want, or 2 times what you want, or half what you want, okay, as long as it fits the formula, that's okay, but then try and rewrite it so your f dash is where it should be, and you've taken out the integral some number to make it work. Okay, so there's a few of those that are quite important, so in a minute a few are going to appear on the board, have a go, and then wait till I go through it, and then if you can master those, you're mastering integrals that come up in the A level, which is very important. Here they are, 3 integrals to be getting on with, press pause, and when you've done, press play. Take your time. Okay, so let's see. Important thing is to think which recognition formula applies. Once you've figured out which recognition formula applies, the rest comes into place. So here, it's similar to the one I just showed you, apart from the fact I've switched the sign and the cos around, which one has the power, which makes a difference. So look, I've got cos cubed 2x. So I've got a function times the power times what seems to be f dash. So we kind of guess it's going to be that. But if we look at it carefully, we've got a few problems. Cos 2x cubed times sine 2x. That's basically what we've got. F of x to the n times f dash. Not so fast. Because if I differentiate cos 2x, I don't get sine 2x. Cos 2x differentiates to minus 2 sine 2x. If your f dash, in what you suspect to be a recognition formula, is only wrong because of a scalar multiple, we can fix that. Just change it to what you want it to be, and then take out a factor to make sure that you haven't changed the integral. So I want this to be cos 2x cubed. I want this to be minus 2 sine 2x. But I don't have that. I don't have the minus 2. Now I've created the minus 2. So how do I undo my creation of that minus 2? To get rid of the minus, I must have a minus there. To get rid of the 2, I must have a half. Just be careful you go the right way round. You don't take out minus 2. You take out minus a half. Okay, think about what you want it to be, and then think about what the factor has to be so that it matches the original integral. Now it fits f of x to the n times f dash with the minus half. So you've got the minus a half there. Then apply the rule. That's f of x to the n times f dash. That f of x needs to turn into n plus 1 according to the formula, which becomes 4, divided by n plus 1. Now sort that out. Minus half divided by 4 is minus an eighth. So the answer is minus an eighth, cos, I'm going to bring the 4 back in, plus c. Okay, there's no powers or anything, so it's kind of leaning towards the first one, which it is. I've got a simple quotient, a numerator and a denominator. If there's no powers involved, just have a quick check. But I differentiate this, I almost get that. I get 7e to the 7x. If I differentiate this, I need to get 7e to the 7x. Which means it's only wrong by a coefficient, wrong by a scalar multiple. I can fix that. So I want that to be, ideally, 7e to the 7x over this. That's what I want it to be. Okay, but I've only got e to the 7x. So let's take out the 7th, then it matches. And not only does it match, but it now is f dash over f. Just be careful to remember the 7th. Then it's ln mod. Once again, mod is not really necessary. Like e to the something is always positive. Plus 5 is even more positive. It cannot be negative. Okay, so you don't need the mod there. Finally, again, we've seen already. Did you see? After you do a few, you get a feel. When you have square root of something on the denominator, okay, if the inside of the square root differentiates to the numerator, subject to a change in constant, then it's going to be recognition number 3. So let's set that up and see what happens. So let's write this as cos 2x plus 3, power of minus a half, times this. Okay, f next to the n times f dash. Or is it? Let's have a look. You can't just assume it's going to hold. F dash would be the differential of cos 2x. What's the differential of cos 2x? Minus 2 sine 2x. I mean, that doesn't look anything like that, does it? Minus 2 sine 2x. I want that to, if we call this f of x, I want this to be minus 2 sine 2x. So let's just think. Is that anything to do with minus 2 sine 2x? Well, something you'll see in integrals is sometimes you have to apply double angle formulae along the path. Is that completely different to that? Sometimes it might be, and therefore none of this stuff applies. But what is minus 2 sine 2x? It's minus 4 sine x cos x, because sine 2x is 2 sine x cos x. So that's minus 4 sine x. Actually, I've almost got that. Again, it's just a coefficient, I'm wrong. That's okay. If I'm just out by a coefficient, we can deal with that. So what I'll do is, I'll stick a minus 4 in there to make it what I want it to be, but I cheated. I've stuck a minus 4 in there. So let's just take out minus a quarter to reverse the cheat that I just did. And now it works. F of x to the n times f dash. So you see a bit of trigonometric identities popping in there. And if that's f of x and that's n, if that's f dash, it's just this, so that power gone up by 1 divided by that new power. That goes up to a half. When you divide by a half, you are timesing by 2. But don't forget, the timesing by 2 then has to multiply by that. Okay, so let's make some space here. Okay, so the f of x is cos 2x plus 3. Pop up the power from minus half to a half, because that's f of x. Divide by a half. But you've also got the minus. If you take out a factor, you must not forget about it. So divided by half becomes 2 on the top. 2 times minus a quarter is minus a half. So the final answer is minus a half cos 2x plus 3 to the half plus c. Job done.